Hi, my name is Kyler Lauderaca. I'm an applications engineer here at Linear Technology. Today I want to talk to you about the newest part in our family of current sense amplifiers, the LT1999. When we started designing this part, we wanted to make a part that would excel in monitoring currents in motors, solenoids, and other inductive loads. Let's take a look at what we came up with. The LT1999 is a precision device offered in 3 gain options, 10, 20, and 50. The gain has a 0.5% accuracy, and the part has a worst-case input offset of 1.5 millivolts. The fixed gain options make designing the part simple and also increase performance in many applications. The LT1999 is a versatile part that can sense bidirectional currents, and with its wide input range of -5 volts to 80 volts, can be used in both high and low side current sensing applications. The wide input range is also important for applications with inductive loads. This is because transients that go above or below the supplies are common. The robust inputs are designed to survive up to a ±60 volt delta, allowing the part to survive open shunt faults, and also enables the part to be used in fuse monitoring applications. One of the most impressive specifications is the 80 dB of CMRR at 100 kHz. This enables the part to reject the large comm mode switching transients that are common in solenoid and electric motor applications. The part also has a 2 MHz gain bandwidth that allows it to accurately monitor the switching current in high-frequency PWM applications. Now that you're familiar with the LT1999, let's take a look at a common H-bridge application. The H-bridge drives a 12-volt brushed DC motor. I want to monitor the motor current to determine both the motor output and the motor torque. Monitoring the motor current will also help to detect faults like a stuck rotor or a damaged drive FET. While all of this sounds good, the H-bridge presents a harsh environment for a current sense amplifier. The H-bridge is controlled by a high-frequency PWM that is typically above 20 kHz. The PWM turns the driving FETs on and off at a set duty cycle, effectively controlling the direction the motor spins, the average voltage across the motor, and the current through the motor. The switching FETs create large comm mode voltage transients with very fast edges across the inputs of the amplifier. This means the amplifier must be fast enough to monitor the bidirectional switching current and also be able to reject the large comm mode voltage changes. Before looking at the LT1999, let's look at a typical approach for monitoring the motor current. For many people, the first thought for this application might be to use an op-amp in a differential amplifier configuration, shown here. To monitor the bidirectional motor current and to stay within the op-amp's comm mode input range, the input signal will need to be attenuated, and the amplifier's input will need to be biased off-ground. The amplifier used will also need a substantial gain bandwidth to provide adequate gain and to be able to monitor the switching currents in the H-bridge. The total gain of this system is set to 20 volts per volt and uses a 25 milliohm shunt. This translates to about 2 amps per volt on the output. The circuit will also use a window comparator to monitor for overfault conditions. The comparator will apply a break signal that will short the motor inputs together if the motor current exceeds a ±4 amp limit. So how does this design work in reality? In the scope photo shown here, I show the diff amp output set to 4 amps a division, a current probe output set to 1 amp a division, and the motor voltage set to 10 volts a division. The current probe is meant to be an impartial measure of the motor current. Looking at the performance of the diff amp, the output is almost unrecognizable when compared to the actual motor current. Every time the motor switches directions, there's a 24-volt comm mode step that causes the amplifier's output to shoot to either rail. This spike produces a false alarm in the protection circuitry, causing the comparators to apply the motor brake, forcing the voltage across the motor to 0. The inability of the amplifier to reject this comm mode voltage change is largely due to the mismatch in the resistor network. With these results seen here, there's really no useful information that can be recovered from the circuit. To improve circuit performance, either closely matched resistors or a substantial amount of trim must be used. Both approaches can greatly increase either design cost or complexity. Another approach might be to filter the output, but this will not work either. The output glitches will appear as DC error in the filtered output. At this point, we will have to redesign the input resistor network, or we could simply use an LT1999. So let's see if I can do better with the LT1999. To design this circuit, all I need to do is pick a gain option and a sense resistor. Typically, the gain and sense resistor combination is chosen to maximize the system's dynamic range and to meet the minimum current resolution requirement of the application. In this case, for easy comparison, I chose a part with a gain of 20 and used the same 25 milliohm sense resistor. All of the input resistors are already built into the LT1999 and are very closely matched, taking care of the most difficult part of the design. Since a gain and sense resistor have been chosen, the design is finished. The part is already set up to bias the output to mid-supply, allowing for bidirectional current measurement. The same comparator circuit will be used to protect the motor from overcurrent faults. With the design finished, let's look at the performance. The top trace shows the output of the LT1999. It's set to 1 amp a division. The next trace is the output of the current probe, also set to 1 amp a division. And the bottom trace is again the voltage across the motor, set to 10 volts a division. The first impression is that the output of the LT1999 very accurately matches the output of the current probe, with no false alarms. The only discrepancies are the small glitches created by the large common mode transients. The glitches settle in roughly 2 microseconds, allowing for accurate current measurement, whether the output of the amplifier is filtered or not. Despite the large common mode transients, the LT1999 is able to accurately measure the current output. With all components trimmed, matched, and built into the package, the LT1999 is about as easy to use as it can be for accurate bidirectional current sensing in a harsh environment. For more information, please visit www.linear.com. Thank you for watching.